questions about the quiz.
Yes, go ahead.
It was the one with the number of components, and then the one with the following sequences are degrees of. They gave us options like A, B, C, and D, and we were to choose which all apply. I missed one of them. I was like back and forth with the one with all sixes. I don't know why, but I second guessed myself and I didn't choose it. Can you explain why it is?
It is relaxed. Oh, okay. Yeah. So, you can see the iPad right now, right? That I'm projecting.
Yes.
I'm lost screen. Yeah. Okay. So, let's see. The sequence of sixes. 1, 2, 3, 4, 5, 6. There were 7, right? 7 sixes. Okay. So here you will have the number of vertices is 7. 1, 2, 3, 4, 5, 6, 7. So number of vertices 7. And all of them of degree 6. So you can just try on error. You can try. Okay, if I have 7 vertices, 1, 2, 3, 4, 5, 6, 7, then and each vertex needs to have degree 6. Then each vertex needs to be joined to everything. Each vertex, and I'm going to use some of the vocabulary we learned. So each vertex is adjacent, meaning it's joined by an edge to every other vertex. So which graphs behave like that? Where all the pairs are joined to each other. So those are the complete graphs. The complete graph satisfies that. So if you actually complete this so that every vertex is joined to everything else, this will give you a K6. So that's a complete graph with 6 vertices, and you will have everything. You could actually draw it. You don't need to draw it, but you could actually draw it. So 6. I'm just gonna draw them in different colors from.
I think you forgot one blue line.
I forgot one. Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I think 1, 2. Which one am I missing?
The top point and the bottom left point.
Like straight down 1 to 6.
Yeah, 1 to 6.
1 to 7. Oh, thank you. Oh, yeah. I don't know if I started from 2. Anyways, it doesn't really matter the colors. Let me just to be organized. It doesn't really matter, right? But so I started with this one. That's my first vertex, and then this one I have. I don't know why I went to like number vertex 3, so that I have 5 more, and here I have 4 more, and here I have 3 more, and here I have 2 more, and the last one. So all of those have degree 6. That would be the K6. Again, you don't need to draw it, but just make sure. The only thing right now is we're trying to understand which chains of numbers, like which lists of numbers like these are actually degree sequences of a graph. And yes, this is one. If you see something like this, it means it's regular, right? All the vertices have the same degree. And we said that Kn is in Kn, all vertices have degree. All vertices have degree n minus 1. So their degree sequence will be n minus 1, so on, n times, which is exactly the case of that 66666.
Also use
Yeah.
the algorithm for this one as well, or
Yes, you can use it.
okay.
Yeah. So, you can start with the 6666.
Esther?
Yeah.
According to your notes, it says for K sub 6, then it would be 5 degrees for each
Okay.
vertex. So do you
Okay,
mean
so-
K7?
Yes. K7. Mhm. Yeah. So if you use thank you, Sean. If you use the algorithm, remember we cross the first one out, but that means that we're gonna take one from each of the one off from each of the 6 next vertices. So that's a 6. So 1, 2, 3, 4, 5, 6. I'm gonna subtract 1 from those. So that's 5, 5, 5, 5, 5. And then I reorder, but they're already in order. So I cross that one out. I have 1, 2, 3, 4, 5. So I need to subtract 1 from from all of them. So I get 4s. And same, I might reorder, but it's already ordered, so I don't need to do that. I cross out the 4. I need to subtract negative. I need to subtract 1 from the next 4 vertices, which is all of them. Now I get 3s. I reorder. It's already ordered. I cross that out. I need to subtract from those 1. So that gives me 2, 2, 2. And remember, once you get to a graph that you recognize, a degree sequence that you recognize as a degree sequence of a graph, you can just go back. And it can be at any moment. If you recognize one, then you're done. This one, I guess it's easily recognizable, but this one is just a triangle. Although 3 vertices of degree 2. But if you still don't recognize it, you can keep going. Now subtract 1. That gives you the 1, 1. 2 vertices, both of degree 1. So just start like that. But you could have started from from this one. And actually, if you here, you just because you can construct that one, you know that all of those are constructible. And so all of these are degree sequences. You don't really need to find the graph. You already know that there is a graph, even if you haven't shown, a picture of the graph. You know that there is a graph. You're done. It is a degree sequence of a graph. But if you want to recover the graph, then the algorithm tells you, start with one of them, with the one that you can construct, either this one or that one, and then to go back to construct the one that you need, you look at, here we erase the vertex that's supposed to be adjacent to these 3. So it's supposed to be adjacent to 3 vertices of degree 2 in my previous graph. So that would be a new vertex. So that would be like this vertex right here. That's joined to vertices of degree 2 in the previous graph, which is actually all of them here. And then this vertex is supposed to be joined to vertices of degree 3, 4 vertices of degree 3 in my previous graph. I have only 4 vertices and all of them had degree 3. So that would be this. And then when I add this vertex, it's supposed to be joined to 5 vertices of degree 4 in my previous graph. 1, 2, 3, 4, 5. All of them have degree 4, so all of them. Here and here and there. And finally, that one, degree 6, joined to 6 vertices of degree 5. 1, 2, 3, 4, 5, 6 vertices, all of them degree 5. So it's joined to everything. Here and here and here and there. And this is actually K7. Just, it looks different than the one that I drew, but I could have constructed, you see, on purpose, I use the same colors. I start with a triangle, then a vertex joins to those 3, and so on. So there are several things that you can do. Graphs, same as with counting combinatorics, is a lot about getting familiar with the concepts and with the graphs. The more graphs you know, the more graphs you've seen, and you find all different properties about them, the more you will be able to go quickly over the problems. So remember, your typical graphs will be complete graphs, cycles. We're going to see something called complete bipartite graphs very soon. Those are graphs that have two parts, and everything on one part is joined to everything on the other part. So we'll see other families, and that way you'll have more toys to play with, in the world of graph theory. All right. The other question was, I guess, this one about. There was a question that looked like this. What is the largest possible number of components? So let me just label them. I don't know what numbers these are, but just as different problems. Or you know what? Let me do it in a different page. So largest number of components in a graph with n vertices, 15 vertices, and minimum degree 3. Okay, so look, we want to have as many pieces, like separated, disconnected pieces as possible. But we have this restriction that each vertex has degree 3 or more. So each vertex needs to be connected to at least 3 or more vertices, right? Which means that this vertex and those 3 vertices and possibly more vertices are going to be in the same component, right? Because a component is a subgraph where you can go from any vertex to any other vertex. And so once two vertices are connected by an edge, they're in the same component. Right? There's like an equivalence relation. If they're connected directly or through other vertices, then they're in the same component. So all of those need to be in the same component. This means that each connected component has at least 4 vertices, right? Because once a vertex is there, its 3 or more partners are also there, or neighbors are also there. So each component has at least 4. And so I want the largest number of components. So that means that if I'm lucky, I can leave it at 4. That's my best bet, right? If I want the largest number of components, I want my components as small as possible. And so if I'm lucky, I can leave that at 4. And so any other component would have at least 4 more vertices, 4 vertices, 4 vertices, and so on, right? But I only have 15 vertices. And if I actually have 4 components, this will give me 16 vertices, right? So I cannot have 4 components. If I'm lucky, I can have 3 components. That's the largest I can. And then you'll see that in graph theory, especially when you're looking for a maximum or a minimum, you have to. It's like, I don't know if you remember from your analysis or calculus class when you're talking about the largest minimum or the supremum. I don't know I don't know what classes each one of you has taken, but if you're taking analysis, when you talk about the supremum, or you have to prove 2 things. You have to prove that something is a bound, and also that it's the smallest one of your bounds or the largest one of your bounds, or whatever it is. So here, we're not being too formal. I didn't mean you to be any formal just yet. We're just exploring. But you'll see that we'll get to problems where you have to show, okay, like in this case, it cannot be 4, but can it really be 3? So you need to give an example that actually has 3 components. But in this case, we were not looking for that. You could just say, okay, you could guess it's 3. It cannot be 4, definitely.
Yes.
And yeah.
And we use theorem, sum of degrees equal twice the edge. Can we use the theorem somehow?
Mm-hmm.
Can we
You
use
could use it. You could use it, but that will give you a bound on the number of edges, right? So let me give me 1 second. Let me finish with this, and then we'll go to your question about how would we use it, or what would that say? What would that say in terms of this problem, right? So so usually what you do is provide an example that actually has 3 components. If you do that, then that's the largest, right? If you feel like with a big probability it's gonna be that 3 components, that's your answer. But that's definitely the largest you could do. We're not at this point, we're not sure that we can do it, but it's the largest you can do. Okay. So, but again, typically you give a possibility, and one possibility, you see, if I want to keep, I need to have 15. So here I only have 12 vertices, right? If I actually had size 4, I will have 12 vertices. I could do, look, if I do a K4, that's the smallest that I can have. That's one component, and the minimum degree is 3. I could just leave it by itself, and that's it. I could have another K4. That's another component. Mm-hmm. And so I have 8 vertices so far. And then I can have a K7 if you want. The only restriction is that I have minimum degree 3. This one will have degree 6. But so it satisfies. We already have a vertex of degree 3. All the vertices have degree. These vertices have degree 3. These vertices have degree 3. These vertices have degree 6. So this is a graph with 15 vertices. 8 plus 7, 15 vertices. Minimum degree delta. Remember that we use lowercase delta for that. Minimum degree 3, because that's the smallest of all those numbers, 3 and 6. 3 and 6s. And 3 connected components. So we can actually find a graph with 3 components. Okay? So here, this shows that there cannot be 4 or more components, and this shows that you can actually do 3. Because maybe there wasn't, for another reason, maybe we cannot have 3, and then the largest will be 2, right? So we're saying, no, there's no other reason. We can actually meet it. And this is not the only example. There are other examples. Mm-hmm. I just need to make sure that all the vertices have 3 or more, or degrees 3 or more. Mm-hmm. Okay. Any other questions? Oh yeah, the degree, the sum of the degrees, right? I said we'll go to that other question. Think of other questions, but I'll talk about this one. So the sum of the degrees, twice the number of edges equals the sum of the degrees of the vertices, right? And we know that each degree is so vertices. Each degree is at least 3, right? So each of these terms has to be 3 or more, because the minimum degree is 3. So all the degrees are 3 or more. Mm-hmm. And here I have 15 vertices. Here I have 15 vertices. That was given, right? So I have 3 plus 3 plus 3 plus 3 in this sum. I have 3 plus 3 plus 3 15 times. So this gives me 3 times 15, which is 45. Mm-hmm. So what we get is that if I divide by 2 in both sides, it just tells me that the number of edges is at least this. So this is 22.5. So E is greater than or equal. It cannot be 22.5. It has to be It has to be an integer, so it has to be at least 23 edges. This doesn't tell me anything about the components. That's the issue. So for this problem, it doesn't help me. But maybe for other problems, if they ask you, for example, what if I ask you what's the largest number or what's the smallest number of edges that a graph with 15 vertices and minimum degree 3 has or can have? Then you would say the smallest number is 33. You will still need to find a graph that actually has 23 edges. But anyways, you see, it gives you a bound. It gives you a bound in the number of edges. This might help you with other problems, but not here. But it doesn't help here. But it's a good illustration of how you could bound number of edges. Here I was asking you to bound number of components, but if I had asked you to bound the number of edges, so this is a proof that the number of edges is at least 22. I could give you a problem that says, prove that in a graph like this, the number of edges is at least 23. There is your proof. So other problems, for example, prove that a graph with 15 vertices and minimum degree 3 has at least 33 edges. Yeah. So it will help you for something like this. If you want to bound edges, you can use that. If you have something given about the degree and the number of edges, then you can always bound on the number of edges. Okay. Any other questions?
Just to clarify, so would you want to say it has at least 23 edges, or just prove that somehow you can get 33?
Sorry, 23.
Okay, just making sure.
And my typos. No, thank you, Scott. Yeah, this is 23.
Because otherwise you can just show that it falls in between 23 and whatever the max is too, right?
Yeah. So you may use other things. For example, sometimes they give you the minimum degree and the maximum degree. Together with this theorem, you can find a bound. And then you can refine your bounds by, we talk about parity of the number of degree vertices, the number of is always even. Sometimes you can use that to just refine your bounds a little bit, or maybe they gave you some other properties so you refine them even more. But usually this relates degrees to number of edges, right? So if you need bounds in the number of edges or bounds in the degrees or something, for example, if they give you a number of edges, maybe they told you something about some degrees and they ask you for the minimum degree or for the maximum degree, this might be helpful. Okay. Wait a second. I haven't checked on the exam for the date for the exam. Was it really set for next week? Are we that behind? Very good. I just saw in the chat. That's true. That's next week. Huh? No, it's not gonna be next week. Let me plan. Let me plan. Let me see what we can do for the next exam, and I'll talk about it on Thursday. I didn't realize it was so close. Right? Thank you, Shin. So we'll talk about the exam, but it's definitely not next week. Okay? All right. Okay. So any other questions? All right. So let me continue with this section, and I want to get to graph isomorphisms. So hopefully we can do that today. This is actually the last part of, I guess, the last theoretical part of this section. These are ways to represent graphs with matrices, and they could be really helpful because anything you know about linear algebra could become handy. We're not going to do as much, but we're going to see a couple of theorems regarding adjacency matrices and graphs. So if you have a simple graph like this, there are two matrices that you can associate to it. The adjacency matrix is the most common one, and the incidence matrix. The incidence matrix, to me, is not as helpful. I know a lot more applications of the adjacency matrix, but it's a way of organizing. For example, for computer algorithms, it's a good way to organize your graph. So this is just essentially saying, these are my vertices, these are my edges. This is just a representation of that edge. So computer-wise, in terms of computer algorithms, this is one way to represent your graph that might be helpful. But mathematically speaking, I think the other one is much more helpful. Anyways, so here, you list the vertices in any order you want, you list the edges in any order you want, and then you're going to write ones if the vertex belongs to the edge for that entry. For example, here I have the entry, this entry is C, AC. The vertex C is part of the edge AC. Or zeros if it isn't. So AB will have ones in A and B, AC has ones in A and C, BC and B and C, CD and C and D, all the others are zeros. So this one is easy. Again, I don't use it as much. The one that I use all the time is this one. This is the adjacency matrix, and so we'll focus mostly on this one. What this one is you list the vertices in any order you want, and here you list the vertices in that same order. So it's an arbitrary order, but the same on both sides. And then you're going to write a 1 if in the entry if the vertices are adjacent, and a 0 if they aren't. So this 1 means that you have the edge BC. This 0 means that you don't have the loop BB. This 0 means that the edge AB is not there, and so on. So here I have my 4 vertices, A, B, C, D. Just list them in some order, same order over here, and I have the edge AC. So I have A, C, that's a 1. And because here the order doesn't matter, the edges are on ordered pairs, then this AC is also represented, that edge is also represented as CA. This one is the same as that one, is the edge AC. And then the edge AB is this one. AB or VA in my matrix. This edge, CB, is this one. CB or BC. And this one, CB, is this one or that one. All the others are zeros. So you can see that I don't need the picture to know things about my graph. I can just work with the adjacency matrix. So for example, what are the degrees of my vertices? The degrees, I can see them here. The degrees are 2, 3, and 1. Degree of A is 1. That is the number of lines that come out of it, which means that if I just look at the row for A, it's adjacent to B and it is adjacent to C. So the number of ones in the row is the degree. So here, number of ones in row A or column A, right? And so you can see C, for example, I can look at row C, and it's the number of ones there. Or you can think of it as the sum of the entries. No? The sum of the entries, 1 plus 1 plus 0 plus 1 is the degree of C. Mhm. So sum of the entries, so maybe I'll say also sum of the entries. Mhm. Okay, so sum of the entries in the first row is a degree of A. Sum of the entries in the second row is a degree of B. Third row, degree of C. Last row, degree of B. So what's the total sum of the entries in the matrix?
Is it 8?
8. And so that's the sum of these numbers, right? 1 plus 2 plus 2 plus 3, 8. So that's the sum of the degrees, the sum of all the degrees. We have a theorem for that. What's the sum of all the degrees? We just use it here. The sum of all the degrees. Uh-huh. Go ahead.
Twice the edge.
Twice the number of edges, right? So the sum of all the entries in my matrix is twice the number of edges. Mhm. So that's related to this question over here. So the sum of the entries in a row is the degree of the vertex labeling that row, right? And so the sum of the degrees is the sum of all entries in the matrix is the sum of the degrees, which is twice the number of edges. Mhm. So that's for the adjacency matrix. In the incidence matrix, the sum of the entries in each row is 2 because it's just the 2 vertices that form the edge. In each column is 2. In each column is 2. And here this is also the degrees. 2, 2, 3, and 1. Okay. So sum equals degree of A, degree of B, degree of C, degree of D, per row. Mhm. Here per row or per column you have the degrees, and here per column is just 2 because it's just the 2 vertices that form the edge. Anyways, so you could also use adjacency matrices for multigraphs, where you allow multiple edges joining the same pair. What that means is that now instead of only ones, you may have twos, threes, larger numbers, depending on how many multiple edges you have joining the same 2 vertices. And if you allow loops, then you're gonna have numbers that are not 0 in the diagonal. But for simple graphs, the numbers in the diagonal are always 0 because you don't have edges joining a vertex to itself. Anyways. So later on, you'll see we'll use the adjacency matrix, for example. We talked about paths, right? The paths, the number of, you can count the number of paths that go from A to B, and or from A to C or things like that. We will be able to count those by multiplying, like raising the number of paths at a certain size have to do with raising this matrix to a certain power. So there is a nice relationship between the paths in the graph and the powers of this matrix. So I think that's one of my favorite applications. Like every application of adjacency matrices. We'll see that later. But for now, this is mostly notation and vocabulary. So that's essentially all we're going to do. you can practice with this problem. It should be pretty easy. Just find the both matrices for that graph. Any questions so far? Okay, so here are the problems. You can put the problems for this section. You can take a look. There are a few other definitions in between. Like, for example, here you have the diameter, the distance, and the diameter of a graph. So it's supposed to be like that, it's part of the problem. These are actually standard definitions, but they are defined here for you. And then there's some experimentation here, exploration here. You should probably go over some of those, see if you understand those definitions. Here you can see 8.7 is the problem that we just went over. It actually tells you that the number of components is at most 3. Okay, so this is the problem that we did earlier today. Oops. So this one, we did it earlier, but this one actually says prove that, right? So I was just looking for the number. Here you actually have to prove that the number of components is at most 3. So you have to, here, we already did it, but because it says prove that the number of components is at most 3, you have to argue that there cannot be more than 4 components. And that was the explanation that each component has at least 4 vertices. Just in case, I'm talking about this problem we went over, right? That's exactly the same problem. 15 vertices, minimum degree 3. So it's just that same problem. 15 vertices, minimum degree 3. And it's asking about the number of components. So you have to argue that there cannot be more than 4 or more components. And that was my first argument, that each component has to have at least 4 vertices, so you cannot have too many components. And then you actually need to show there is a graph with 3 components. So what I was telling you, you actually need to show to be considered a proof. You have to argue you cannot do more than 3, so 4 or more, and you need to show that you can actually do 3. Okay, so you need to provide a graph with 3 components, which we do. Okay, so that's a proof. You can try some of this. I'll keep picking some of these problems to go over in class. Take a look. And in fact, what we can do is, take a look, and at the beginning of next class, you can tell me, which problems you would like to see, which one of the ones where you had the most trouble, and we can go over them. We can spend a little bit of the class on that, and then we can keep going with other topics. So there's plenty of exercises. Take a look. It's very important because this is what will get you, familiarized with all the concepts and some strategies. Anyways, questions? So let me go to section B. If you think of something else to let me know, okay? But I'll go to section B, which is isomorphisms. This is a very important section, and hopefully it will make sense to you. The proofs can be, for some graphs, very easy, and for others, complicated. So I'll show you what I mean. I'll upload everything later today. So this is section B. It's a very small section, but some of these proofs can be challenging. So here we talk about equivalent graphs. Equivalent graphs actually have already labels, and you have to check that you actually have the same pairs of vertices joined with edges, right? So like here you have AB, here you don't have AB, so these 2 graphs are not equivalent in the sense that we defined them before, right? So these 2 are not equivalent, as it says below, but I want to say why. Not equivalent because A is adjacent to B. I'm trying to use more vocabulary. It's again going to be G1, let me call this one G1, and let me call this one G2. But A is not adjacent to B. And G2, right? So equivalent meant that you had exactly the same pairs joined by edges. And here, let me just say, I'm just going to add something here. We, to defining equivalent graphs depends on the labels, right? So if they don't have labels, we cannot say anything about being equivalent, because to be equivalent means that the labels kind of match, right? So, but however, they look the same. So if I remove the labels, they are the same graph, right? They look completely the same. They are the same graph. It's just this. So, but we're lucky in a way that they are drawn in the same way, because I could have had, maybe it wouldn't be as clear if we had one of them drawn like this and the other one drawn like that. I don't know, Maybe to me they look the same because I've seen these graphs many, many, many times, but maybe to you they just don't look the same. Mm-hmm. But these two are equivalent. Well, I don't want to use the word equivalent because we used it for label graphs, but all of these are really the same graph. Mm-hmm. Just one vertex joins to another, joins to the next, joins to the next, And how do I make sure? How do I mathematically make them the same? I will say that they are isomorphic. Okay, so all of these are isomorphic. And how do I prove that they're isomorphic? I label them. I find a way to label all of them using the same labels so that they are equivalent. Okay, so for instance, I can label this one 1, 2, 3, 4, just because it's the easier one. Right? Any labels you want. And I want to label the other two so that they are equivalent. So I have exactly the same pairs joined to each other. So I need to have 1 joined to 2. 1 has degree 1, right? It has to be like the starting point. Clearly, 1 needs to be this one or that one, right? The starting point of my trajectory, I guess. So I can do it in 2 different ways, but essentially, I just need to find one way to do it. 1, 2, 3, 4. And now you can see that they are equivalent as label graphs, right? And same with this one, 1, 2, 3, 4. And I can do it in 2 different ways. But I just need to find one way to label them so that they're all equivalent, right? So we kind of use the word equivalent when the graphs are labeled, and that's easy to check because you just check that all the pairs are. Even if it's 100 edges, you would just have to check 100 things, right? So algorithmically speaking, there's nothing to it. You just check the pairs. But when you have drawings with no labels, then it's harder. You need to find the labeling. Okay, so for some graphs it's very easy, but for some others it's not. And if you want to go over, like kind of a little bit more precise definition, you'll find it here. But that really is what it means. 2 graphs are isomorphic if you can relabel one of them to match the other, to be equivalent to the other. So many times you have labels in your graphs, and they might not be like in this one, In this one, for example, these 2 are not equivalent with the labels that they have. But if you want to show that they are equivalent, you just relabel one of them to match the other, right? And to me, sometimes it is easier to say, let me just use different labels so I don't get confused. 1, 2, 3 instead of A, B, C. But in reality, I could just kind of scratch these ones and decide what's going to be A, B, and C, and leave the others as they were. I could say, okay, A needs to be the beginning. I'm going to still leave this one A, and then this one B, and this one C. You kind of scratch one of the labels, set of labels, and use the other if you want. But to me, it's easier to just just use different labels for both of them. Forget about their original labels. And then they will be isomorphic. So here you can see that these graphs are isomorphic. If I completely forget about the labels, are they the same graph? Forget about the labels. They're asking for isomorphic, not equivalent. So it doesn't really have to do with the labels. The labels can be misleading. If they are equivalent with the labels that they're given, then they're isomorphic. Perfect. But maybe they're trying to mislead us, the labels. So forget about the labels. Do you think that those two graphs can be labeled in a way that they are equivalent? Yes, right? It's just like we twisted the square.
Can we think about the same edges and same vertices as long as they have the same number of vertices and edges?
That's actually a very good comment. Is it enough that they have the same number of vertices and edges? That's a good question. That's the first question. Is it only the number of vertices and edges, or is there more to it? So quick answer, no, it's not enough. You need to look at other things. But we'll get to some of that. Just give me a few minutes. Okay, so here I said, many times the labels are misleading. In this case, we actually have exactly the same pairs: A, B, A, B, B. Well, we don't have the same pairs. You see, A, B is there, but then I have B, B, and here I don't have B, B. So you can say, that these two are not equivalent with the labels that they gave us, right? Because here I have BB and here I don't have BB. Yeah? So they're not equivalent, but they are isomorphic. And to show that they're isomorphic, you can just relabel one of them or just label both of them so that they're equivalent. Again, I prefer to just start with new labels so I don't get confused with the A's and the B's and what I need to change. But you can do that if you want. So 1, 2, 3, 4, 1. I kind of follow my cycle, right? So they are isomorphic. So find new labels to know them. Equivalent. So they are isomorphic, they're not equivalent with those original labels. So it says, what about this ones? Well, let's see, A, B. Let's see if they're equivalent first. A, B is joined to A, B. I actually have the triangle A, B, C, A, B. I don't have CA. Right? I have CA here, and I don't have CA here. So again, these are not equivalent because I have AC here, and I don't have AC there. So they're not equivalent. Now, are they isomorphic? So isomorphic means that they're essentially the same relationships, but maybe drawn in a different way. So can I find labels that make them equivalent? Okay. So how would I do that? Well, let's go back to that question. Then having the same number of vertices and same number of edges make them equivalent? I mean, isomorphic? And I said no, but if they don't match, they're definitely not isomorphic. So let's see, I have 4 vertices and I have 4 vertices here. I have this, I actually need to have the same degrees. If they're isomorphic, they need to have the same number of vertices, the same number of edges, the same degree sequence. the same number of cycles of a given size, the same number of paths of a given size. All of those things need to happen. So if you find one of those that doesn't happen, then they're not isomorphic. But finding one of those when they're not isomorphic can be tricky. So this is actually a really hard problem. So of course, when you have small graphs, it's not necessarily hard, but in general, it's a really hard problem. So in this one, because I know that the degrees need to match, let me look at the degrees. Okay, so I'm gonna write the degrees here. So those were my labels. I guess I should have been using numbers. So these are not degrees, these are labels. These are gonna be degrees. Okay, so I have degree 2, degree 2, degree 3, and degree 3. And in this one, I have degree 3 here, degree 3 here, degree 2, and degree 2. So the labels for the degree 2 vertices need to be the same in both, and the labels for degree 3 vertices need to be the same in both. So I'll use W, X, Y, Z as my labels. Okay? So I'm going to use W for this one, and I'm going to use X for that one. So this one needs to be W, and there's one of them W, and the other one X. Mm-hmm. And then I know that W is joined to, let me make this one Y and Z. So it's arbitrary on one side, right, on one graph. And then I can figure out which one of those needs to be Y and which one needs to be Z. So W is joined to Y and Z, so no difference. And X needs to be to Y and Z, no difference. I could just, it doesn't matter if I write YZ in the other one or ZY. It's gonna work. And then you can check that you actually have the same part, the same case. So I have WY, WZ, WY, WZ, ZY, ZY. Mm-hmm. So maybe I can highlight this. So ZY is right here. And then I have these two, and these two. And then I have these two, and these two. So now they're equivalent, so they're isomorphic. Yeah.
So the answer to both of the graphs on the left is yes, they are, because we can change them.
We can change the graph, right? We change the labels. So two graphs are isomorphic.
Are we allowed?
Yes.
Are we allowed to change it, or you're showing an example?
We're allowed to change them to prove that they're isomorphic. We're not allowed to change the labels if we already gave. If the graphs come with labels, then we use the word equivalent, right? We use the word equivalent, and we're not supposed to change the labels. We're supposed to go with those labels, okay? To prove that they're equivalent, we use those labels. To prove that they're equivalent or that they aren't, we use the labels that were given to us. To prove that two graphs are isomorphic, we completely disregard whatever labels they gave us, if you want, so completely disregard them and just relabel them. You can use the same labels if A, B, C, D if you want, but you can choose whichever labels you want and just label both so that they become equivalent. Mm-hmm.
So they would ask, is it equivalent or not? We will say no, but if it is, if they ask if it's isomorphic, we will say yes.
Yes. So they're not equivalent, but they are isomorphic. And same for this one. And the proof that they are isomorphic, the proof that they're isomorphic is right here. We found labels that made them equivalent. Same thing here. Two graphs are isomorphic if you can label them to make them equivalent. So this is one possible definition of isomorphic. Because you are allowed to label them, you can use whatever labels you want. In some of the exercises, you'll see, I'll give you one graph already with labels, and then you have to relabel the other one using those labels, right? So I kind of, I could have said here, okay, I'm going to use W, X, Y, Z. Now I need to figure out which is W, which is X, which is which. So I can just use arbitrary labels for one of them and figure out what are the where to place the labels for the other to make them equivalent. Mm-hmm. So okay, so let me see. Maybe I can find, yeah. So for example, here, show that these two graphs are isomorphic. What I was just talking about is you can just arbitrarily label one of them. I can say A, B, C, X, Y, Z, whichever labels you want. And then you need to figure out where to place the A, the B, the C, or the A, B, C, X, Y, Z here. Okay? So it looks like all the vertices here behave the same way. So I can arbitrarily say this is going to be A. And then here, A is joined to A, to Y, and to Z. So that means that this, I don't know which, but this needs to be X, Y, or Z. This needs to be X, Y, or Z. And this needs to be X, Y, or Z. But I don't know which one is which. Because here, in order to make them equivalent, A is joined to X, to Y, and to Z, and these are the only three edges that come out of there. So each one of these needs to be X, Y, and Z, but I don't know which one's which. And, you can, right now we don't have a technique. And actually, there's no algorithm to figure out if two graphs are isomorphic. That's kind of the issue with this problem. But, I can try. I'm just going to say try. Let's try X, Y, and Z. Let's see if I can complete that. And then one of the other two vertices has be B and the other one C. So I'm going to try making this one B and see what happens. Okay? So let's see. B has to be joined to X, to Y, and to Z. B is joined to X, to Y, and to Z. Perfect. So far so good. The other one will need to be C. And here C is joined to X, to Y, and to Z. Z is joined to X, Y, and Z. Perfect. It was trial and error. Not completely. We use some information. We assigned that arbitrarily. We knew that these ones have to be X, Y, and Z in some order. We just pick one and see what happened. There is where the trial and error started, but we knew they had to be X, Y, and Z. And then we also picked this one just to see if it worked, and it did. So in that sense, it was trial and error, but we at least knew that those three, these three need to be X, Y, and Z, and the others two need to be B and C. Okay, so here, classify each statement as either true or false, and each assume that the graphs are labeled. So now you only have labeled graphs. All complete graphs are equivalent. So for all complete graphs are equivalent. You see, I can give you two complete graphs that are like completely different. Regardless of the labels, the base set assumes that all are they equivalent? Are these two equivalent? No, right? So this is false because I can have different sizes. I can have a huge graph and a small graph, and those definitely don't have the same number of vertices. And to be isomorphic, they need to have same number of vertices, same number of edges, same degree sequence, and same of a lot of things. Okay? So all complete graphs with the same number of vertices are equivalent. All complete graphs with the same number of vertices. For example, I don't know, A, B, C, X, Y, Z. Remember that they say that the graphs are labeled. So they gave us the labels. Are these two equivalent?
No.
No, they have different vertices. right? So no. Are they isomorphic?
No.
Not really.
This is true. So complete graphs with same number of vertices. So for example, if I take all the complete graphs with 3 vertices, are they isomorphic?
Nope.
Well, you're referring to which then, yeah, right? For this one?
Are we referring to what, sorry?
For the triangle or?
Yeah. So as an example, right? Because it says same number of vertices. So I'm just taking the example number of vertices equals 3. Just to understand the problem. So number of vertices equals 3. All the graphs with complete graphs with 3 vertices, all of them really are just like the cycle, right? I can draw it in different ways. Maybe like this. This is another one of those. But then the question is, are those isomorphic?
I would,
Regardless of the label.
I would say yes, because the last example has the same amount of vertices.
Yeah. The isomorphic, remember, the fact that they're labeled doesn't matter anymore. Because isomorphic means that we can forget about the labels and relabel them ourselves to make them equivalent, right? So, yes, these are isomorphic. All the K3s are isomorphic. All the K4s are isomorphic. All the K5s are isomorphic. Because you can always relabel. I can show you, for example, sorry, let me go back to, oh no, I don't have it here. Remember that I had my K7 in that example about the degree sequence 6666 drawn into different ways. You can always relabel the vertices. You see, even if they tell me this is ABC and this is XYZ, I could take these, when I'm trying to prove that they're isomorphic, it's okay for me to remove the labels and then relabel, right? So I remove the labels and then I relabel in any way I want. So I can make this A or something else, maybe CVE, and I can make this one CVE, and I will have all the pairs are the same. CV, VE, and EC. So they are isomorphic. All the K3s, all the K4s, all the K5s, all the K6. And I can show you, for example, here's a K5. So here's a K5. That would be like the most typical way to draw a K5. And here's another K5. So I just need to make sure that all vertices are joined to, or pairs of vertices are joined by edges. There. So there's another K5. And I can label, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And you can actually check my highlight edges. I have 1 is joined to 2, to 3, to 4, and to 5. 1 is joined to 2, to 3, to 4, and to 5. In fact, as long as they have the same set of labels, it doesn't matter which is which, it will be fine because 2 is joined to everything else. 3, 4, 5. 2 is joined to 3, 4, 5, and 1, which I already checked, that one, and 1. Mm-hmm. And then I also have 3 to 4, 3 to 4, and 3 to 5. 3 to 4, 3 to 5, and I also have 4 to 5, 4 to 5. You see? So, and it doesn't matter how many vertices, I will be able to do that. So all of them are isomorphic. And so for the last two, all cycle graphs with the same number of vertices are equivalent. Same idea. All of them are just like a cycle, but maybe it's twisted and, made into a knot. But they are essentially like a ring, right? Of the same size. So all of this, and that's where we need my isomorphic. They're essentially the same thing. You can just untwist it and make it look like a ring, like a polygon or regular polygon. So all of them, and psychographs was same vertices. Oh, sorry. I made a mistake here. So they are isomorphic, but they're not equivalent because it depends on the labels that they give us, right? So false, and this is true. This is false. I can use the same. You see, this was K3, but I can use the same example here. I can do it with C3. That's K3 and C3 are the same thing. As label graphs, they can have different labels, and so they will not be equivalent. That's why this is false. Because they can give me just different sets of labels and they won't be equivalent, but isomorphic, they always are. So that's the difference between isomorphic and equivalent.
Is there anything different when it says cycle graphs?
Yes. So C4s all look like squares, but we say that this is isomorphic to that, right? The drawing, those two are isomorphic. Maybe I won't use that symbol just yet. So they're isomorphic because you can relabel them, and essentially, how would you relabel them? You can, you get started at some point, wherever you want, and you just follow the cycle, right? 1 goes to 2, 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 4, 3 goes to 4, and 4 goes to 1. And you will have it. It doesn't matter how big it is. You can always relabel them to just follow the instructions to close that cycle. So you can have C5, which will be a pentagon, or some modification of the pentagon. C5 is a hexagon, or some modification of the hexagon. You can draw them in many different ways. So, for example, C6 can look like that. That's kind of the most typical way to draw C6. But you can also have anything crazy, 1, 2, 3, 4, 5, 6. I can have 1, 2, go here to 3, and then go back here to 4, and then go here to 5, and then 6, and then back to 1. That's another C6. I can do it in a different way. As long as I kind of keep a ring twisted and not there or something, then it will be a C6. And that's the idea of isomorphism. They are really the same graph, just different drawings of the same graph. And instead of saying the same graph, we say, they are the same graph, but you really say that the two drawings, the two graphs are isomorphic, because for these are kind of, for some of them are pretty easy to see, but for others are not. So one thing is here. If two graphs are isomorphic, then they have the same number of vertices, same number of edges, the same maximum degree, minimum degree sequence, number of components, same diameter, which I told you please read in those exercises. They have essentially the same thing of everything. So for those things, if you find two graphs that have different number of vertices, or different number of edges, or different minimum degree, or different maximum degree, any of those things are different, you can automatically say they're not isomorphic. But if they have all of those things they have in common, then how can you prove that they're not isomorphic? If they are not, if they are, you can try to find the labeling, but it's not necessarily easy. For example, here, it says, show that these two graphs are not isomorphic. Not isomorphic. So let's see. We can check number of vertices. This one, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They have the same number of vertices. Number of edges. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. Number or let's say degree sequence. Let's see. This is 1, 1, 1, 2, 2, 3. 1, 1, 1, 2, 2, 3. They have the same degree sequence. 2, 2, 2. 1, 1, 1. Same degree sequence. So If one of those happen to be different, you say they're not isomorphic. But if they are the same, no conclusion. You need to keep looking for something else. So here you will see this. Not only they need to have all those same things, they also need to satisfy that, because we are going to relabel them. A vertex of degree 3, if a vertex of degree 3 is joined to a vertex of degree 2, there will be also a pair in the other graph where a vertex of degree 3 is joined to a vertex of degree 2. If a vertex has neighbors of certain degrees, then there should be another vertex in the other graph that has that same degree and its neighbors to vertices of the same degree, and all those things, right? So, for example, here I can look at the vertex of degree 3, and it is joined to vertices of degree 1, 1, and 2. But here, the only vertex of degree 3 is joined to vertices of degree 2, 2, and 1. Which means that if I try to relabel them, I will be in trouble. Because whatever labels I use, whatever label I use for this one needs to be the same as for that one, because those are the only vertices of degree 3. So they need to have the same label, right? But then whatever labels I use, if I use labels X, Y, and Z for the vertices of degree 1, then I need to make X, Y, and Z these ones, right? Those three need to be in some order. They need to be X, Y, and Z, right? But then here I have AX and AY, and here I will only have either AX or AY, or maybe none of them, because I only have, only these vertices X, Y, or Z. So these two graphs are not isomorphic. The way you can say is just, what I highlighted. Non-isomorphic because the neighbors of A, which is my vertex of degree 3, have a different set of degrees. Different sets of degrees. Meaning here I have, let's say this is G1 and this is G2. The sets of degrees are 1, 1, 2 in G1. 1, 2, 2 in G2. Okay? So, in words, you could say something like that. You can rephrase it in many different ways. But essentially, what we notice is that the vertex of degree 3 here is not joined to the same kind of vertices as the vertex of degree 3 there. Okay? So they're not isomorphic. Questions? All right. So we'll continue next time with isomorphisms. Keep looking at these problems. See how many of those you can solve, especially these first ones. You're going to see that, again, this section, we essentially cover everything about isomorphisms, but we need to see many other problems because all the problems kind of look different. Next time we'll go over B5 through B10. And then, so take a look at these other ones. See if you have questions on them. See if you can solve some of them. So I will assign some of them next time. But, take a look. Let me know. And we'll go over the others and whatever questions you have. We'll finish with isomorphisms next time. And then I'll tell you a plan for what's next. All right?
Thank you.
Okay, guys. I'll see you next time. Thank you so much. I'll be in my office hours at 2 if you have any other questions. Right?
Thank you, Professor.
I have a quick question. Do you have time now?
Yeah.
Go
ahead.
It's the question of the days. Are they considered like extra credit, or they're just like regular quizzes, basically?
Well, they're part of your grade. It's just like an easy part of your grade, right? Because I only had 2 questions of the day. I may have another soon, so I think of them as easy credit. Not
Okay.
extra credit, which I count on you doing them, but they're really supposed to be very, very easy, right? It's just that you take the time.
Yeah, I was just wondering because we already spoke that I missed the first one because I didn't know it was due the same day. But I was just wondering if they're extra credit or they're counted towards the grade.
They're counted.
Okay, got it. Thank you.
Professor, do we have a what's it called? The Section A wiki problems that we're supposed to do?
No, I haven't assigned anything. Let me plan for the exam to have everything on for the exam, and then I'll let you know what we'll do. We have the quiz for question A, and then we'll have something else that will have isomorphisms.
Nice.
But then I'll figure out exactly. Let me just figure out the timeline so that we have time for
Okay.
everything. Okay.
Thank you.
Okay. So
Thank you.
I'll give you a plan on Thursday.
Okay, sounds good. Thank you, Professor.
All right. Thank you, guys.
Thanks, Doctor.